Hi, this is Dr. Morgan over at Clovis East High School. Let's get started with today's lesson. We're going to begin a unit on exponents. We have had an introduction to exponents when we did geometric sequences. You remember those are the ones that are growing not by adding a number or subtracting a number, but by multiplying or dividing. So the sequence doubles or triples in that case. We want to look at this now not as sequences, but as a function. As we start, I'd like to give you an example of how exponential functions can work. This is a fun example. You see, a man asked the boy next door to mow his lawn. When the lawn was completed, he asked the boy how much he owed him, and the boy said, I'll give you two options. Option one is you can just pay me $10 for mowing your lawn, or option two, we'll do a payment plan. You pay me 1 penny today, 1 cent today, and then tomorrow you double it and you'll pay me 2 cents. The next day and the third day you'll double it and pay me 4 cents, and then 8 cents, and each day we just double the amount for 30 days. How much do you think the man would pay if he chose the second option? Well, here I've done a graph showing you, a table showing you exactly, you notice here, first day, 1 penny, 2 pennies, 4 pennies, 8 pennies, 16. By the end of the 10 days, he's getting paid $5 that day. Now, if you look back there, that means if you added them all up, he's probably got his $10 in the first 10 days. But notice as it keeps doubling, surprising, 10, 20, 40, 81, 160, 300, 600, 1,013, and we get into 21. Now we're at 10,000, 20,000, 40,000, 167,000. By day 30, the man would be paying him just for that day $5,368,709.12. And if you added all 30 days up, the man would have paid over $10 million to have his lawn mowed. That's what we mean by things growing exponentially. Notice the first couple of days, it doesn't seem like much, a penny, 2 pennies, 2 pennies, 4 pennies, 8 pennies. But if you keep doubling it, it gets big in a hurry. This next slide is from our, it's called the average rate of change. This should look somewhat familiar to you because when we have a linear equation, the average rate of change is simply the slope. So you notice here to find the average rate of change between two x's, a and b, I find the f of b and subtract the f of a and divide by b over a. That should look familiar. That's the change in y over the change in x. And when we do this on a line, it's called a slope. However, when we do it on a curved line, as we're going to be doing in this chapter, you see we're just giving an average over that range. It's not always the same. So we want to compare what's the difference between a linear function and an exponential function. So we have two graphs here. Notice first of all the equation. The equation for a linear function, we've seen this all last semester, y equals mx plus b, where m is the slope and b is the y-intercept. You notice that when we graph it, it graphs as a straight line. We call this a first order equation because it's x to the 1 power. The key thing there is on equal intervals of the domain, the differences are constant. For example, if I have these numbers here, notice what's the same is they go up by plus 3, plus 3, plus 3. That would be the sequence, the arithmetic sequence. But the point is there's a common difference there. When we move over to the exponential function, look at the equation. Now the x is actually up in the exponent. All right? The a is kind of like our b in the first one. It's kind of the y-intercept. And b is what's it being multiplied by or divided by. Okay? In this case, what's constant isn't a constant difference, but constant ratios. So in this sequence here, for example, notice what's happening is we're not adding 3 each time, we're multiplying by 3. And that's the difference between a linear function and an exponential function. You can sometimes, if you have any equations, you can look up here and say, where's the x? If it's like mx plus b, it's linear. If the x is in the exponent, you've got an exponential. If you see a graph, is it a straight line or a curved line? How is it growing? If you take different angles there, different intervals, is it growing by adding or by multiplying or dividing? So as you look at our first couple examples, how do I tell whether these are linear or exponential functions? Remember that a linear function has the form equation y equals mx plus b, and an exponential function, the x is up in the exponent. Y equals a times b to the x function. Now notice up here it says y equals 3x. Which one does that match up to? Notice that is a y equals mx plus b. In this case, b is 0, but I have x multiplied by 3. So this is a first order equation. In other words, it is a linear function. My next one, though, notice again the x is up in the exponent. It's subscript. It's up above. It's superscript. So it has the form y equals a times b to the x, 3 times 6 to the x. So this is an exponential function. The equation has the variable in the exponent. That's what tips it off for you. Again, 3 and 4. If I look at remember again, I need to keep in mind, what's a linear function look like? Y equals mx plus b. What's an exponential function look like? Y equals a times b to the x. So look at number 3. Which form does it look like? Look at the x. Is it in the exponent, or is it sitting with a coefficient? In this case, notice this is negative 2 times x plus 1. That should say, oh, that's like mx plus b. So we know this is a first order equation. This is a linear function. When we go to the second one, we see the x, but it's up in the exponent. It's 3x, but don't let the 3 mess with you. The x is in the exponent. So it's of this form. Y equals a times b to the x. So we have here an exponential function. The variable is in the exponent. Now in number 5, they didn't give us an equation, they gave us a table. So we have to look at how is this thing growing over equal intervals. So I see it's growing by over equal intervals, meaning the x values, it's 1, 1, 1. So how is this growing? I always start by seeing, is it being added or subtracted? So notice from negative 1 to negative 3 is goes down negative 2. But then between negative 3 and negative 9 is negative 6. Between these, negative 18. So obviously this is not a linear equation, because if it was linear, we'd be adding or subtracting the same number. So let's look at the ratio, the common ratio or the multiplier. So notice if I take, it goes from negative 1 to negative 3. So negative 3 over negative 1 is 3. All right. If I take the next one, 3 times there, negative 18 divided by negative 6 is 3 again. In other words, what I have here is this number is growing by being multiplied by 3. That means it's an exponential function. On equal intervals, the ratios of consecutive values are constant, which wasn't the case here. Well, it was the case here for the ratios. So notice the ratio between each of them is the same. Negative 3 over negative 1, negative 9 over negative 3, negative 27 over 9. They all equal 3. In other words, as x increases by 1, y increases by multiplying by 3. This is an exponential function. So let's try this again on the next table. Again, making sure that our intervals are the same. We notice that 1, 2, 3 is going up by 1. Let's see what's changing down below. From negative 1 to positive 1 goes up 2. 1 to 3 is plus 2. 3 to 5 is plus 2. It's just adding 2 each time. When you have that, we have a common difference between the two numbers, and that means this is a linear function. On equal intervals, the differences of the consecutive values are constant. 1 minus 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. Constant difference, common difference, that makes this a linear function. Let's continue on with number 7. Again, the interval is 1. So do we have a common difference? I look at that first because it's easy to spot. 6 to 9 is up 3. 9 to 12 plus 3. 12 to 15 plus 3. So we have a common difference of plus 3. So this is a linear function. You see 9 minus 6 is 3. 12 minus 9 is 3. 15 minus 12 is 3. A common difference is a linear function, which, by the way, in this case also turns out to be the slope, because 3 divided by 1 is your slope. All right, let's try again. We have our consistent interval of 1, 0, 1, 2, 3. So let's see how it is. What's the difference between them? If I go from 40 to 20, 20 minus 40 means it went down minus 20. But 10 minus 20 is minus 10. So notice I do not have a common difference. It's going down by a different amount each time. So let's compare the ratio of the two numbers. Instead of subtracting them, let's find the ratio. And notice if I take 20 and divide by 40, I get 1/2. So what I have here is a common ratio. 40 times half of 40 is 20, half of 20 is 10, and half of 10 is 5. So what I have here is an exponential function. This time it's being multiplied by a half, or you could consider that the same as being divided by 2. So on the same equal, see 20 divided by 40 is 1/2, 10 divided by 20 is 1/2, and 5 divided by 10 is 1/2. That's what we call the common ratio or the common multiplier, an exponential function. In the next one, we have an actual word problem. It says a population of 10 tadpoles, that's what it begins, triples every week. So is this a linear function or an exponential function? Once again, even though the tables turn sideways, we still look at the weeks, 1, 2, 3, equal intervals. How's it changing? Notice 10 to 20, it went up 20, but then it went up 60, and then it went up 180. So immediately we know this is not a linear function. Let's check and see if there's a common ratio. So for example, my common ratio would be, it went from 10 to 30, so 30 divided by 10 is 3. So our common ratio may be 3. Let's just check it out. 10 times 3 is 30. 30 times 3 is 90. 90 times 30 is 270. So yes, the population triples every week, and that means that the ratio will be constant 3, and the growth of the tadpoles is an exponential function. In our next problem, it says we have Abby who earns $16 per hour, so we're going to track her total earnings. So in the first hour she earned 16, the second hour she earned 16 again, so now she has $32. Then she earns 13 again. Notice what's happening here is each time, because she works one more hour, she gets 16 more dollars. So each time her earnings are increasing by 16. So when you have something that's going up by the same amount, you have a linear equation because there's a common difference. 32 minus 16 is 16. All right. Since Abby earns $16 each hour, that means the difference in her pay between consecutive hours will be constant, 16 hours. This is a linear function. In problem 11, we have a culture of bacteria. Starts with 1,200 bacteria, and the number of bacteria is halved each day. Halved means to cut in half, or you could say divided by 2. So as I look at the difference first, I see first one, it goes down 600, but then it goes down 300, and finally it goes down 150. So because there's not a common difference, the difference is not the same, this is not linear. Is it exponential? Let's see if there's a common ratio. So if I take 600 divided by 1,200, I see that's 1/2. And if I look there, I can see 1,200 times a half is 600. Half of 600 is 300, and half of 300 is 150. That means that since the culture is cut in half each day, there is that constant ratio, 1/2. So this is actually an exponential function. It's just an exponential decrease, decay, as opposed to growing or growth. In problem 12, it says that a student takes out a $1,000 simple interest loan at 5% annual interest rate. This is kind of an important problem because later on we're going to talk about a different kind of interest called compound interest. In simple interest, you only earn money on the principal that you first put in the bank. In compound interest, you earn interest on the principal and any interest you had from prior years. So in this case, he takes out a loan for $1,000, and every year he pays 5% of $1,000. So the first year it's $1,050, 5% of 1,000, and then he had another 50. So each year he's paying $50 for the original 1,000 that he had. Notice that we have a common difference. And so this is a linear function. We're going to discover when we get into compound interest that that's going to be an exponential function, because you're not only just paying interest on the original principal, But each year you pay interest on the interest that you owed from the previous year. Lots of times in a simple interest like this, what's happening is every year that you have the loan out, you just simply pay them back the interest until whatever time you feel like you're able to pay the whole thing off. In our next problem, it says that Sandra gets $12,000 car loan with a 5% compounded interest. So at the end of the first year, 5% of $12,000 is $600. So now she owes $12,600. But what's happening each time here is now it's not the next year. It's not just add 600 because that would then be 13,200. But we have 13,230. So this isn't being added. Instead, it's being multiplied by 1.05 each time. In other words, my common ratio each time is 1.05. If I take year 2, 13,230, and divide it by year 1, I get 1.05. You see that percent again? 5% is I get 100% the next year plus 5%. So in this case, the loan balance increases by 5% of the principal and interest. And so the ratio is 1.5. This is an exponential function. So this is going to grow a lot more than just that simple interest. Simple interest in this problem would mean every year I just add 600. But here, every year I add 600 plus interest on the interest. That's what makes it compounded. So here we have another word problem. Tom pays $350 for rent every month. So what's his accumulated rent? Notice here, $350 the first month, then he pays $350 the second month, so now he has $700 he's paid. Then $350 again, and $350 again. So obviously we have a common difference as we're accruing rental of $350. So since the amount of rent increases by the same amount each year, that's a common difference of $350. That means this is a linear function. All right, we want to talk a little bit at the end of this lesson about average rate of change. We saw in our vocabulary before, over the interval x is between a and b, the average rate of change is what's the function at value b minus the function at value a divided by b over a. The average change is a lot like finding the slope. Now when we have a linear function, the rate of change is constant. No matter where I pick along the line, if I pick any 2 points, the average rate of change will always be the same. However, when I have a curved function like an exponential, notice what I'm going to be doing actually. The reason it's called an average is because if I pick any 2 points, like see the blue line crossing here, between these 2 points, I'm actually finding the slope of the blue line between there, and I'm calling it the average rate of change along the red line between those 2 points. But notice if I pick 2 more points, okay, now I have a slope here. Notice that the average rate of change here is smaller in the first one than in the second one, because if you think about it, as a curve changes, the slope of the line is actually changing. So we're just trying to find the average rate of change between 2 points, which is actually the slope of the line between those 2 points. So I want us to compare the average rate of change between an exponential and a linear. Notice first here, number 15, f of x equals 5 of x minus 2. We look at the equation and we see that's clearly a linear function. It's in the mx plus b formula. And if I actually take points 0, 1, 2, 3 to 6 and put it in, I get the points negative 2, 3, 8, 13, 18, 23, 28. Notice it's growing by 5 because my slope is 5, and that's our red slope there. All right. On the other hand, if I were to graph 5 times 2 to the x, notice here 2 to the x is 2 to the 0 is 1, so it's 5, 10. Notice what's happening. Each time it's being multiplied here by 2. 5 is where it starts, the a, but the b is what's it being multiplied by. So 2 times 5 is 10, 2 times 10 is 20, 2 times 20 is 40, etc. And we get the blue graph that looks like here. That's an exponential function. So let's look on the next graph and see how to find the average rate of change for these. So let's find the average rate of change for the linear function. F of x equals 5x minus 2. First, let's remember what our formula is here. f of b minus f of a over b minus a. Where here in the first kind, what we're looking here is saying we're talking about a and b. When a, in other words, we're going from a to b, so we're going from here to here, or from here to here. So the f of b is the y. So f of b, you see, is 8, and f of a is minus 2. So I end up with 8 minus a minus 2 over b minus a, which is 2 minus 0. Remember that 8 minus a negative 2 is going to become 8 plus 2, or 10. And so my rate of change there is 10. Now when I go from 2 to 4, I'm going from here to here and from here to here. So notice my f of b there, I'm going to have 18 minus 8 on top and 4 minus 2. So once again, I get 10 over 2, or 5. And then between 4 and 6, when I go from 4 to 6 and I go from 18 to 28, again, my formula 28 minus 18 over 6 minus 4, and I get 10 over 2, which is equal to 5. In other words, notice that the rate of change is constant, and that's a feature of a linear function. It's a constant all the way through. All right, so let's try our average rate of change idea again for the exponential function. F of x equals 5 times 2 to the x. Let's remember again what our formula is. It's that slope formula again, but this time it's a curved line. So notice when I go between 0 and 2, I'm going between here and here, and then over here is my this is f of a, f of b. Remember, the first one is my a, the second one's my b. So when I look at this on the y side, I have 20 minus 5 over 2 minus 0. So I end up with 15 over 2, or 7.5. Now when we move down to 2 and 4, I'm going between 2 and 4, and then on the y side, 20 and 80. So f of b then becomes 80 minus 20 over 4 minus 2, so I have 60 over 2, or 30. Notice that my rate of change grew significantly from 7.5 to 30. Let's try our last interval between 4 and 6. Between 4 and 6, it goes from 80 to 320. So now I'm going to have 320 minus 80 over 6 minus 4. And I end up with 240, ends up to be 120. So notice what we expected. The rate of change is increasing significantly. The rate of change is not constant, it's increasing. And that's because if you remember the curve continues to grow steeper and steeper, and that's what the average rate of change is showing us here. So finally, if we compare the data side by side, notice on the left side, f of x equals 5x minus 2, you see the linear line, and you see that the average rate of change between 0 to 2, 2 to 4, and 4 to 6 is always the same. It's the slope of the line, 5. On the other hand, when you go to the exponential, you see that the rate of change between 0 and 2 is 7.5, between 2 and 5 is 30, between 20. That's reflecting the fact that the farther we go along on the blue graph, it gets steeper and steeper. The rate of change is not constant, it is increasing. That's a sign of an exponential function.